In this lesson, we continue talking about sets, and we're going to learn how you can perform operations on sets. Now, just in case you don't know what I mean by the word operation, I want you to know that you've already seen plenty of operations in your life. For example, you know that 3 plus 4 is the same thing as 7. Well, plus is actually an operation. The idea behind an operation is that an operation takes two things on either side and then converts them into something else. So for example, the plus operation converts 3 and 4 into the number 7. And we're saying we'd like to actually perform operations that act on sets rather than numbers. So I've started here with a picture of two different sets, A and B. And in this case, as you can see, A and B actually have a certain area where they overlap. I want you to imagine that these are sets of jelly beans. This is a blue jelly bean and a pink jelly bean, and so on. Well, the set A contains all the flavors of jelly beans that Alice likes, and the set B contains all of the flavors of jelly beans that Bob likes. And as we said, a set operation is going to combine two sets, like the set A and the set B, to form new sets. The simplest way to combine this set A with this set B is to actually take what we call the union of the sets. The union of the sets is going to take any jelly bean that either Alice or Bob likes. So it's going to contain all 6 of these jelly beans. So to make this as clear as possible, this new set that we just drew is actually the union of these two sets A and B. So we can draw it as this whole area over here. Now, because it is the union of the two sets, it's going to contain every single element that's either in A or in B, as we just said. So it's going to be a new set that contains red, yellow, green, blue, pink, and purple. So the set union is usually denoted by this symbol, and I guess you can remember it because it looks a little bit like a U. In a sense, the set union is going to unite both of the individual sets into a single large set, and therefore it's going to contain all of these elements that I've shown here. So if the set union is going to contain all of the jelly beans that both Alice and Bob like, well then we have another one called the set intersection that tells you all of the jelly beans that both Alice and Bob like, and that's going to be these two in the middle. Sometimes it helps to think of the intersection as having every element in both A and B. And therefore you can say that the union has everything in either A or B. And therefore, we can easily see that both the green jelly bean and the yellow jelly bean are enjoyed by both Alice and Bob, and they are the only two jelly beans that both of them like. Now, before I move on to the next operation, I want to show you something special about the union and the intersection. Whether you're looking for the jelly beans that Alice or Bob likes, or the jelly beans that Bob or Alice likes, of course you're going to get the same jelly beans. So the idea is that whether you write A or B, or you write B or A, you're still going to get the exact same thing. The same thing goes for AND as well. Whether you want the jelly beans that Alice and Bob likes, or you want the jelly beans that Bob and Alice likes, of course you're always going to be talking about the exact same jelly beans. In a sense, this is very much like the way addition works. For example, you know that 3 plus 4 is the same thing as 7, but then 4 plus 3 is also 7. So whether or not you write 3 plus 4 or 4 plus 3, you're always going to get the exact same answer. However, the story isn't quite the same when you think of subtraction, right? If you go 3 minus 4, you're going to get minus 1. But then if you do 4 minus 3, you're actually just going to get 1. So, at least for subtraction, the order in which you put the things that you're going to subtract, which we call the operands, actually does matter. The order of subtraction matters. Now, the counterpart of subtraction for sets is this thing we call the relative complement. Let me just explain what it is to you before writing anything about it. The relative complement of A and B is actually the same thing as taking all the jelly beans that Alice likes and then removing the jelly beans that Bob likes. Or in simpler words, the relative complement of A and B includes all the jelly beans in A without the jelly beans in B. So we define the relative complement to include everything in A without anything in B. And therefore, it's going to start with all 4 of these jelly beans and remove these 2, leaving you only with the blue and the pink jelly bean. Usually, we write the relative complement with this symbol over here, a backslash. Sometimes you will find people writing it with a minus sign as well, so they just write A minus B. But I prefer not to do that because it may become confusing when you aren't really sure whether you're dealing with sets or numbers. By using this symbol, it makes it very clear that the 2 things you're operating on are actually sets. Now, because it's possible to take everything in A without B, then isn't it also going to be possible to take everything in B and then remove the things in A? Well, it is. So, unlike the union or the intersection, swapping the order of things actually does matter when you're talking about the relative complements. So if A without B starts with all of A and then removes the elements in B, then B without A is going to start with the elements in B and then remove the elements in A. So in this case, B without A is actually going to contain this red jelly bean and this purple jelly bean only. So as we see, A without B contains the blue and pink jelly beans, which we can see here. And then B without A contains the red and purple jelly beans, which we see over here. And therefore, you cannot actually swap these 2 because if you do, you're going to end up with a completely different set. Now, as you can see, given 2 sets A and B, the union, intersection, and the 2 relative complements are all of the operations that we can perform on these 2 sets, because they include every possible combination of sets and every possible subpart of these sets. Now I want you to imagine for a moment, however, that there were some jelly beans that neither Alice nor Bob actually liked. There are some jelly beans that neither of their sets needed to include. So in this universal set of jelly beans, we have all the same jelly beans that Alice and Bob liked, but we have this new jelly bean, this orange one, that neither of them actually seem to like. Now, a universal set doesn't always actually exist, but in some contexts, a universal set actually makes sense. For example, this brand only makes these flavored jelly beans, and therefore these are the only jelly beans that you could possibly have in these sets. Now, aside from Alice and Bob, I want you to imagine that Chris gets to choose their favorite jelly beans as well. They're going to choose this yellow, red, green, and blue jelly bean. Now, I want you to imagine actually applying these different operations to Chris and the universal set. So we can start by thinking about the union of Chris's set and the universal set. Well, we would say that that's the same thing as Chris or the universal set. But if we wanted all the jelly beans that are either members of Chris's set or the universal set, I want you to realize that they're all inside of the universal set anyway. So therefore, Chris or you is the exact same thing as you. And if you think about it, that actually makes perfect sense, because any jelly bean that Chris likes must also be inside of the universal set. So Chris or you is the exact same thing as the universal set. Now, something similar happens when we consider the intersection of the universal set and Chris's set. If we wanted all of the jelly beans that are members of both Chris's set and the universal set, well, that's only going to include the jelly beans that Chris likes, because all of these jelly beans are going to be excluded. So therefore, if you think about it, Chris's set and the universal set is just going to be the same thing as Chris's set. Because the only way that a jelly bean can be a member of Chris's set and the universal set is if it's inside of Chris's set. Because if it's in Chris's set, it's already inside of the universal set. So therefore, the union and the intersection of Chris's set with the universal set are actually reasonably straightforward. However, by defining a universal set, we actually get one more set operation that I should tell you about. So by adding on this universal set, we get this new thing called the total complement. And the total complement is just going to be the universal set without Chris's set. So if we started with every single jelly bean and then removed the jelly beans that Chris likes, well, that just leaves us with a set of jelly beans that Chris does not like. So when we write this bar on top of C, we are assuming that there is actually a universal set. And you can actually read this as the set not C. Or in other words, it's the jelly beans that C doesn't like. But aside from this, I think we're ready to review everything. I want you to imagine that we started off with two sets A and B that contain a bunch of jelly beans. A contains blue, pink, green, and yellow, whereas B contains green, yellow, red, and purple. The union of these two sets is going to include every single jelly bean that's in either set. So it's going to contain blue, pink, green, yellow, red, and purple. On the other hand, the intersection is going to include only the jelly beans that are in both of the sets A and B. So that's only going to include this green and yellow jelly bean, as you can see over here. We said that A or B is the same thing as B or A, and A and B is the same thing as B and A. But then we also defined the relative complement, which does not have this property. A without B is not the same thing as B without A. We said that you can form A without B by starting with everything in A and then removing the things in B. So you're only left with the blue and the pink jelly beans, as you see here. On the other hand, B without A tells you to start with B and then remove the things in A. So therefore, you're only left with the red and purple jelly beans, as you see here. In certain situations, but definitely not all of them, it is possible to define this thing called a universal set that contains every possible element that you could even put into a set. If it does make sense to have a universal set in your context, then you can start to actually perform operations with your new set and the universal set. So we said that if you wanted the elements in either C or U, then of course that's going to be the same thing as U. If you wanted the elements that are inside of both C and U, well, that's only going to include the jelly beans that are inside of C. But then, when you think about the relative complement, we actually do have one more thing in our arsenal. We can say that not C is the same thing as the universal set without the elements in C. So in other words, you start with every jelly bean and remove the jelly beans that Chris likes. So therefore we'd say that the total complement, which some people just call the complement, includes every jelly bean that Chris does not like, which are these three over here. Now, as you might imagine, when you first learned about numbers, they didn't really seem that important, right? But when you started to realize that you could add them and subtract them and do things like that, they became much more useful, because you could actually operate upon them to create new objects that were useful to you. And the exact same thing goes for sets. If you're going to operate on sets, you can make new sets that might represent something that you actually care about. Now, throughout your studies of mathematics, you're going to be forming a whole heap of new sets. And by being able to operate on those sets, you're going to be able to form any kind of set that you might need to solve a particular problem that you'd like to solve. So now that you know how to actually operate upon sets, in the next lesson, I'm going to show you how you can use these different operations to help you count things that would otherwise be very difficult to count. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.